This video begins a two-video journey over the process of learning about how we can achieve locate queries in big O of R space in a run length compressed full text index. So we've already talked about the count query. That's not the subject for today, not the main subject for today. Today our subject really is the locate query, and why is it that we're able to achieve locate queries efficiently in big O of R space, and we'll get really specific about what is achievable in terms of the exact space and time bounds that we can do for locate queries. So let's get started by reminding ourselves about how we have been doing locate queries even in the non-run length compressed setting. So back when we talked about the standard FM index without run length compression, we had a little bit of a trick for how we answered locate queries. First of all, we said answers to locate queries can be pre-computed, right? So if I do my iterated backward search procedure and my pattern is, say, the string ABA, and so at the end of my iterated backward search procedure I know that these are the rows that begin with ABA, then we could imagine another array parallel to the Burrows-Wheeler matrix that simply tells us, which permutation or which rotation that is in each row of the Burrows-Wheeler matrix. And we said this is the suffix array. This is the exact same thing as the suffix array discussed in other videos. So if we were to pre-compute that answer for every row, we would have computed the suffix array of the text T. We don't want the whole suffix array. That's too big. I mean, the good news is that the suffix array allows us, for every one of these pattern matches, to immediately look up its offset with respect to T. So that's great. We get a good benefit. It's easy to query because everything is a direct lookup in the suffix array. However, it's too big because we need n integers to store it, where n is the total length of the text. So in other words, there's nothing about the suffix array by itself before we do clever things. There's nothing about the suffix array that allows us to take advantage of the run length compressibility of a repetitive text. We weren't even satisfied with n integers before. When we were talking about the FM index, we came up with the idea of subsampling the suffix array, so that instead of keeping all the elements of the suffix array, let's say we just kept some of them. So for example, let's say we kept the even ones. So if we kept the even elements of the suffix array, then when it came time to look up the offset of this pattern match of ABA, we would look over in the corresponding element of our sampled suffix array, somehow, this is with some associative data structure over here, and we'd see, oh, we kept a note about what suffix array offset was present for this row of the Burrows-Wheeler matrix, so we get offset 0. But then we go to look up this one, and we find it is not there. And now we have to do something to figure out, well, okay, fine. So we didn't keep that one, but we still have to answer the locate query. So what do? We can do an LF mapping, right? So we find ourselves here in the row that ends with this A, so that's the A of rank 1, right? So I suppose that's the A of rank 0, that's A of rank 1, 2, 3. So we're in the row that ends in the A of rank 1, so we jump to the row that begins with the A of rank 1, that's this row. We've now invoked the LF mapping, which means that what we've done with respect to the text, T, is we've moved to the left by one character. Okay, and then we go look in our associative data structure again, and behold, we have kept that element, so we know that that row of the Burrows-Wheeler matrix is at offset 2 with respect to the text, and therefore we know that in the row we began our search, that row was at offset 3 with respect to the text, right? Because we moved to the left by 1, then found that that rotation was at offset 2. So the original rotation was at offset 3. Okay, and this principle worked regardless of what the sampling interval was, right? So we could have done evens only, we could have done multiples of 4 only, for example. So here I've kept only 0 and 4 as the offsets in the suffix array. That's okay. Even when it comes time to look up this offset here, we just repeatedly invoke the LF mapping until we arrive at a row of the Burrows-Wheeler matrix for which we've kept a suffix array sample, and then add the number of steps we had to take to get to that row. So that general principle we're going to keep, as you'll see. We're going to sort of, generally speaking, keep the principle that we will use sampling. We will have to be clever about the interval we use with respect to sampling, but once we have done this sampling, we'll be able to answer queries within reasonable time budgets, and we only had to keep a sample of the suffix array entries. So to summarize what we've been doing, all right, we've been sampling, right, we saw this already. If we store a sample such that we are taking suffix array entries at multiples of some constant c, like in this example we took multiples of 4, then the maximum number of LF steps we're going to need to take to get to the next, to a row for which we kept a suffix array sample is bounded by c, right? Right. The maximum number of times we'll have to invoke the LF mapping is really c minus 1 before we get to a row, before we are guaranteed to have got to a row that has a saved suffix array element. Okay, so if we pick some constant c and let that be our interval, then we haven't really affected the big O bound, right? C is not some function of n, it's just some constant, so big O of n divided by c, if that's the number of integers we have to store at the end of the day, is still big O of n, right? It's still growing linearly with n because c is a constant. We don't have to pick that to be a constant. We could pick it to be a function of n. We could say, for example, that the interval between these suffix array samples is square root of n, and that therefore means that the number of times we have to invoke the LF mapping before we are guaranteed to get to a suffix array sample is n over square root of n, in other words, square root of n. We have this choice. Even that function of n, though, is a large price to pay if our text is very repetitive and we know, or hope at least, that we could take advantage of that repetitiveness, right? This doesn't really take advantage of repetitiveness in any way, even if we try to make our sampling interval be a function of n. What we would prefer, strongly prefer, what we need really, for repetitive texts is something that depends on r and does not depend on n, or only mildly depends on n. Okay, so for a repetitive text, we want to be able to answer locate queries, but in big O of R space, if we can do it. And if these queries are still efficient after we manage to reduce the space footprint in this way. So before we begin this journey into discussing how to accomplish these big O of R locate queries, let me take a couple of asides to talk through some concepts that will be useful to us later. So first of all, here's a concept that we already intuitively know because it's wrapped up with how we just were describing the process for how to resolve locate queries when we keep a sample of the suffix array. Right? Intuitively, we know there's sort of these two separate spaces, two separate, almost like coordinate systems. One of them is the text t, so just imagine this is the text t. I've oriented it sort of top to bottom, so the text you can imagine is spelled out top to bottom. So there's the text t. And when we live in the text, we think about offsets with respect to the text. We usually use I as our index when we do offsets with respect to the text t. So that's sort of t space, right? When we're talking about t space, we're talking about thinking in terms of offsets with respect to the text. Then over here on the other side, you can imagine we've built the Burrows-Wheeler matrix, we've got our Burrows-Wheeler transform. Everything in that space is now in this new order, right? The Burrows-Wheeler transform permutes the characters of t according to the alphabetical order of their right contexts. So now everything is in a new space, in a way, in a new order, where that order is governed by the alphabetical order of these right contexts. And I'm going to call this, for the purpose of this talk, I'll just call it lex space. Lex, short for lexicographical, so it's a little bit like, alphabetically ordered space. So on the one hand, we have t, and we think in terms of offsets with respect to t. And on the other hand, we have the Burrows-Wheeler matrix, and we think in terms of, in essence, ranks, right? Like the ranks of suffixes that are the right contexts of characters within t. T space, lex space. And we have ways of moving in these spaces, right? These are the sort of fundamental ways that we move around. We just discussed one of them, which was the LF mapping, right? There's also a way of translating from one space's coordinates to the other. When we are doing locate queries, we are trying to do a translation from the lex space coordinates to the t space coordinates, and that is what the suffix array does, right? So you could think of the suffix array as one way of encoding the function that gets us from lex space back to t space. We could go the other way too, in which case we use another structure, which is often called the inverse suffix array. I'll denote it with SA with a -1 in the superscript. Sometimes you'll see it referred to as ISA for inverse suffix array, right? So these two things are sort of the functions that get us back and forth. In terms of movement, though, we've been talking about the LF mapping. The LF mapping is something that if we have a coordinate in lex space, let's call it Q, let's say we're at a certain coordinate in lex space, invoking the LF mapping takes us to another coordinate in lex space, right? It takes us to another place with respect to the Burrows-Wheeler matrix, right? The LF mapping, we're very familiar with the LF mapping procedure, right? It's all about jump to the right section, jump to the right character of the rank within that section. It's jumping to another place with respect to lex space. It's not a predictable place, right? Like we're not necessarily, when we use the LF mapping, we're not necessarily going earlier or later or by 1 or by 10, right? It's not really predictable. We're going to, in some sense, an arbitrary new spot with respect to lex space. So let's say we invoke the LF mapping on our original coordinate Q. We got a new coordinate Q prime. We could iterate. We could run the LF mapping again on our new coordinate Q prime. We get a new coordinate Q double prime. Again, that movement is not really predictable in terms of where the new Q prime prime is going to land with respect to lex space. It just goes somewhere else. And we can iterate again. So this is roughly what 3 iterations of the LF mapping might look like with respect to lex space. What's interesting is to bring in the idea of how these movements using the LF mapping in lex space are reflected in t space. And we already know that they represent movements to the left by 1. Right? That's what this sort of equation is denoting. The suffix array entry at the LF of Q is equal to the suffix array entry at Q minus 1. Right? The suffix array being the way we translate from lex to t coordinates. So it's a little bit like the LF mapping moves in lex space in a way that corresponds. So an LF step in lex space moves in a way that corresponds to a movement to the left by 1 in t space. So 1, 2, 3, pictured here on the slide, look a bit like this. 1, 2, 3, if pictured in t space, right? We're just moving to the left by 1, or in this picture, I guess we're moving up by 1 because I arranged t vertically. Okay, so there is, for an LF movement in lex space, there's a corresponding predictable incremental step movement in t space. That's just the nature of the LF mapping. That's what it's doing. And that's also why it's useful to us here with our sampling procedure. We need to know if we iterate the LF mapping by 1, it means we move to the left by 1 with respect to t. So if we've done anything in terms of keeping hints for ourselves in the coordinates of t, spaced a certain way, the fact that we're moving to the left by 1 with respect to t is quite nice because we can create guarantees that it won't take too many steps before we get to a destination. As an aside, there's another function not called LF, it's called phi. So for some reason we use a Greek symbol for this function, the symbol phi. Phi you can think of as just being another function where instead of being potentially large arbitrary movements in lex space that correspond to predictable movements in t space, incremental predictable movements in t space, phi's the opposite. So phi is that we're jumping from place to place with respect to t, and the way we are jumping is that we are jumping, if we jump from one spot to another, it's because we jumped from a spot that had a certain lexicographical rank, whose right context had a certain lexicographical rank, to another place whose right context has the next lowest lexicographical rank, whose right context has the next lowest lexicographical rank. You can just think of it as almost the mirror image of LF. It's not the inverse of LF, mind you, right? It's not, because it's not even about movement. It's not about the same kind of movement, so it's not the inverse of LF. It's, in some sense, a mirror image, right? So we're making movements in T space that correspond to predictable incremental movements in Lex space. Okay, but that was just an aside. I suppose it's also worth mentioning that both LF and phi you can think of as having inverses, where instead of corresponding to leftward movements in the other space, they correspond to rightward movements. So you can imagine something that undoes the LF mapping, that goes backwards across the LF mapping, would correspond to rightward predictable stepwise movements in T space. Likewise, we could imagine an inverse phi function which corresponds to rightward predictable incremental movements in Lex space. Okay, so all of the things that we are going to do are going to correspond to movements in one space or the other, and it is helpful to keep this kind of picture in mind. The suffix array is the function that moves in the Lex to T direction. The inverse suffix array moves in the other direction. The LF corresponds to predictable incremental movements in T. Okay, the final point I want to make before I start in on the Toehold lemma is to do with what the LF mapping looks like when the text is repetitive. When the text is repetitive, the LF mapping kind of operates in a what I'll call runny way, right? So here's our favorite example of a repetitive text T. Pictured here. Here's its Burrows-Wheeler transform. Here's the sort of F, right? If this is the last column of the Burrows-Wheeler matrix, this is the first column. And if we were to picture what the LF mapping does to the characters of a, let's pick a character, in this case we picked R. If we imagine what the LF mapping does to all the R's with respect to L, well, it maps them all onto F in a very kind of consecutive way, right? There's a lot of consecutivity here, right? All the R's in this bunch map to a consecutive stretch of R's on the other side, right, with respect to the F column. Likewise, all the R's in that second run also LF map in a consecutive way. So it's like the LF mapping is mapping, we of course can think of it as mapping individual characters. You know, we can think of all the arrows that I've drawn on this slide, or we can think of the LF mapping as operating on essentially a block or a run of characters. And so instead of all those individual arrows, one way, an alternate way I could represent it is to draw this whole big parallelogram shaped thing, saying this whole chunk goes to that whole chunk. You know, this whole chunk of L goes to that whole chunk of F. When the LF mapping is runny, that means that what the LF mapping does to a particular character in a run and what it does to another character in the same run is kind of parallel, right? Represented by these parallelograms. Okay, I could draw all the parallelograms all together in one picture and it looks like this. A little bit chaotic, but anyway, that's in some sense a totally complete picture of what the LF mapping does for this repetitive text, and it doesn't require n parallelograms, it only requires r parallelograms. So, okay, so like I say, if we focus in on the letters of one run, the LF mapping is doing something kind of parallel to those same run letters. And the principle that we could write down is we could say, okay, well, if the BWT at offset q and the BWT at offset q plus 1, right, so two adjacent letters in the BWT, are the same letter, if they're the same letter, right, in other words, if they're part of a run together, right, so if two adjacent elements of the BWT are the same letter, then that means the LF mapping of the first one and the LF mapping of the second one are still going to be right next to each other when they move, right? The LF mapping of q plus 1, the one on the right, is equal to the LF mapping of q, the one on the left, plus 1. Right? You go over by 1 and go down is the same as going down and going over by 1. This is true if they are the same character, if they're together in the same run. If they are different characters, then they're not part of the same run, and this bet is off, right? They could go to completely separate places with respect to the F column, right? They're going to go to different letter sections, right? So it doesn't work if BWT of Q is not equal to BWT of Q plus 1. So two positions in the same BWT run move through the LF mapping in a parallel fashion. Okay, these are the principles we need before we can examine this Toehold lemma. So now let us get started. We are going to talk about the algorithm that achieves big O of R locate queries, and our algorithmic concept here has two components to it. The first component is going to be about, during the backward search procedure, keeping a bit of extra side information that will be important to our query. Particularly, we're going to keep this thing called a toehold, which is our ultimate goal is to know the suffix array entries for all our matches, but a toehold means we just know the suffix array entry for one of our matches so far. Okay, so that's what the toehold is. We just keep track of one. And then the second part of the algorithm is going to be that the toehold is enough, because from the toehold we can do another kind of query to figure out the rest later on. Okay, the second part of this conceptual framework will have to wait for the next video, but we will tackle the first part here. Okay, so let's do the first part. And if I can, let me harken back to, we were saying that we want to keep a sample, but we want to keep an amount of suffix array information that grows with R. So let's start with a simple, obvious suggestion for what we should keep in our suffix array sample. I'm going to suggest that what we keep in our suffix array sample are the suffix array entries that are at the beginnings of the runs. Right? A little bit like in the previous lecture when we talked about backward search in the run length compressed BWT, we talked about keeping one letter per run and keeping a bit vector that marks each run so that there's one per run. Similarly here, I'm going to suggest keeping a suffix array sample per run, specifically at the heads of the runs. So here we are, we've got T, we've got L. When we're talking about the runs, we're talking about runs with respect to L, so let's look at L. And let's imagine that for each of those runs, we're going to store one suffix array entry per run. So the first run is that T at the very beginning. Its suffix array entry is 62. I computed that elsewhere, but anyway, its suffix array entry is 62. So we keep that suffix array entry, boom, in some sort of data structure. We move on to the next run. The next run is a run of 3 R's. So for the first R in that run, we keep its suffix array entry, which is 57. Boom. Next run of W's, keep a suffix array entry. Next run of O's. Next run of underscores, etc. And so for every run I've now drawn on this slide a suffix array sample corresponding to what is the suffix array entry for the first element of that run. Simple idea. And obviously it results in big O of R integers, in fact. Exactly R integers, right? There's one integer per run, so we have exactly R integers here on the screen. I am also going to suggest that we keep samples at run tails. So this is not all we keep. We also keep these, right? So now I've just drawn L again, but instead of highlighting the run heads, I've highlighted the run tails. In some cases, they're the same, right? Because some of the runs have length 1, so the head and the tail are the same. But anyway, so there's all the suffix array samples at the run tails. I'm going to suggest we keep both, the samples at the heads, the samples at the tails. And that will be part of how we can keep track of our toehold as we do backward search. So equipped with these suffix array samples, now our job is to augment the backward search procedure so that at every step we know for one of the elements that we're tracking what its suffix array entry is, and we need to be able to update that at each step. So here's the information we have, and here's what we want to do with it. We want to change our backward search procedure. This schematic is showing the old way that we did backward search in the FM index, where we would do step, 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 and then at the end we would take the range of elements that we had matched, and for each of those rows we would do a separate locate query, locate, 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 to figure out what element was there. In our new framework, part of the work of doing the locate query is going to be wrapped up with the backward search. As part of the backward search, we are keeping our toehold. Right? So a schematic of what we're going to do appears here. We need to augment backward search so that at every step, in addition to just knowing this range, right, the sort of range denoted here and denoted here, in addition to knowing that range, we want to know for one of the elements in our range, one of the elements of the BWT in our range, we want to know its suffix array entry. Okay. And we need this to be true at every step. At every step, we want to know the suffix array entry for some element in our range. It actually doesn't matter which one. We just need to know the suffix array entry for one of them so that later we can get the rest. Okay, but that requires that we need some strategy. If we know the value at one iteration, we need a strategy so that we still know a value at the next iteration. So we need to be able to update which is the element for which we know the suffix array entry and what is the suffix array entry that we know. We need to update that at each step. Okay, so shown here is one transition, a transition from step I to step I plus 1. If we assume that we had everything we needed in step I, in other words, in step I we knew some j, in other words, some offset inside our range of BWT characters for which we know the corresponding suffix array entry, SA of j, superscript I. So in step I we have that j and SA of j. And now we want to update for step I plus 1, where our next query character, right, at each step we're matching longer and longer suffixes of our pattern. So let's say as we go to step I plus 1, y here is the additional character that we know. So as we proceed into step I plus 1, we update our range, right? I've got SP and EP standing in for what's the beginning and the end of our range. So we got our new SP and our new EP, but we need somehow to compute our new J and SA of J. And I'm going to argue that to figure out how to do this, we just need to consider two cases. One of the cases is the case where this character is equal to the next character in P. So in other words, this Y matches this character in the BWT. That's case 1. BWT at J of I equals Y. We'll handle that case on the next slide. The other case, of course, is where they're not equal. Right? If you think of one step of backward search, we have one range and then we update it to get a new range. Some of the elements in our original range correspond to elements in this new range. Some of the elements in our original range don't correspond to elements in this new range, according to whether they matched the next character of the query. So we're sort of splitting our discussion up into these two cases, right? Where the row that we were tracking, the row for which we had the toehold, is one of the ones that survives to the next step. That's case 1. Versus case 2, the row that we were tracking did not survive to the next step. And so we need to somehow scramble onto another row and get a new sample in the new iteration. Okay, but case 1 is the easier case. Case 1 is the case where the row that we were tracking, the row for which we had a suffix array sample, survived the backward search procedure, and it's still there in the next iteration. In other words, the case where the BWT character matched the next character in our query Y. In that case, if we want to update J and SA of J, that's not hard because we just need to use the LF mapping. Right? The LF mapping does exactly what we need. LF does all the work. If we take the LF of J to the I, we get LF of J to the I plus 1. We get the new row that corresponds to that same match that we were tracking, right? In other words, we can figure out exactly which row in the new range is the one that corresponded to the old row for which we had the suffix array entry. And the way we update the suffix array entry, SA of J, is also very predictable because we just move to the left by 1 with respect to the text. So the new SA is, the SA of J at step I plus 1 is the SA at J at step I minus 1 because we move to the left by 1. So that case was actually quite easy. How do we update J and SA of J? We just apply the LF mapping to J and we just subtract 1 from the suffix array entry. Easy. So that was case 1. Case 2 is the case where the row that we were tracking does not exist in our range in the next backward search step. That case is a little trickier. We have to break this one down into some sort of subcases. So let's take subcase case 2a. And let's say case 2a is that not only did the element that we were tracking not match the next character in the pattern, but none of the characters in our whole range matched the next character in the pattern. Well, that case is actually kind of easy in the sense that, maybe like vacuously easy, I guess, in the sense that our next range will be empty and our search will have ended and there won't be any matches, right? So there's actually no more work to do. We failed to match the pattern. There's no locate queries to do. So that's case 2a. So that's the case where none of the characters in our range managed to match the next character in the pattern. But case 2b, which is much more interesting, is the case where our range did have some characters that matched the next character in the pattern. It's just that the particular row that we were tracking failed to match the next character in the pattern. The row that we were tracking failed to match, but some other rows in our range do match the next character in the pattern. So that's case 2b. So what do we do in the case of case 2b? Well, let's observe that in case 2b, what we're saying about the BWT characters in our range is that some of them do match the next character in the pattern P, which we called Y. So some of them do match Y, some of them don't. So if some of them do match Y and some of them don't, they might be arranged, let's say, in a configuration that looks like this. So there's some Ys and some non-Ys in that range, right? So I've used red to denote the Ys. Or, you know, maybe it doesn't look exactly like that. Maybe it sort of looks like this, where there's some Ys at the beginning and then some non-Ys after that. Or maybe it looks like this, where there's a Y at the end. Regardless, however it looks, we can guarantee something, right? There's a guarantee that somewhere in there, there's a run head or a run tail for Y. There must be, because if there's a mix of characters and only some of them are Y, then there has to be somewhere in there a run head or a run tail for a run of Ys. Okay, so if we had some way of quickly figuring out where that run head or run tail was, then we could, with those suffix array samples that we kept, because we kept a sample at every run head and every run tail, we could sort of manage to move to that row. Like we'll say, okay, well, no, that row is the one that I want to pick as the one that I'm tracking. So the row that I was tracking, it fell off. It no longer matches, but I can scramble to a different row that does manage to match the query and for which I do, again, know the suffix array sample. Okay, so we know that somewhere in this stretch of BWT characters, there has to be a run of Ys, or there has to be a part of a run of Ys such that we have a run head or a run tail. So we're going to look up the corresponding suffix array entry from our data structure. That's the idea. We have to get a little bit more specific now about what the data structure is, such that we can do that lookup. It's going to look kind of similar to the predecessor data structure that we already talked about from the previous video, but we still need to get a little bit more specific. So how exactly do we look up what this new suffix array entry is that we should use, given that we know somewhere in there, somewhere in that BWT range, there is a run of Ys, and there is in fact a run head or a run tail of a run of Ys. Okay, so remember our discussion of the predecessor structure. We used this in the previous video to accomplish part of our run length count query backward search procedure. You know, we reviewed that there is a way, if the bit vector that marks the run heads is sparse, then there are ways that we can represent and query it in a way that keep the space requirement to big O of R and don't really break the bank, don't really use a whole lot of time. And we picked one very simple way to explain it first before we talked about the more complicated way to do it. And the simple way involved building this array here that we called S1, which has the answers to all possible select queries. This turned out to be a good way of doing predecessor queries. And if we want to not only do predecessor queries, right, we not only want to be able to jump to the previous, let's say, run head or tail with respect to the BWT, if we also want to associate some data with that run head or tail, that's actually not so hard to add into this picture. So we have our array S1 with our answers to all the select queries. An idea would be if we want to associate values with those answers to those select queries, which might correspond to the run heads and tails, we could store another array parallel to S1, right? So for example, if this was an array of suffix array samples, we might call it SSA for sampled suffix array, we would just arrange that array parallel to S1 and then it would contain some associated data. So this is how we can associate suffix array samples with the run heads and tails. So given that we can do this, we can do it with whatever data structure supports these kinds of predecessor queries. And as we already discussed in the previous video, that simple idea that was on the previous slide, yes, that will work, but there's also literature that shows maybe more efficient ways to do it, including this blue, this bit here, the predecessor data structure that we used previously that achieved log n over r time in O of r space. We can essentially use that same data structure here to allow us to do these predecessor queries on the run heads and tails and to retrieve that associated bit of data, which is the suffix array sample at that run head or tail. There's just one more detail, which is that when we do this query, we're not just doing it on all the run heads and tails. We actually are doing it with respect to a specific alphabet character, right? Like in the example I showed before, we weren't just interested in jumping to the head or tail of any run in the range. We were interested in jumping to the head or tail of a Y run. So we need some way to be able to do this query specifically for particular alphabet characters, right? So like, for example, if our alphabet consisted of A and B, and we wanted to be able to do predecessor queries and get associated data, but we wanted to be able to do it separately for A run heads and tails and B run heads and tails, then we might do it with a data structure that looks like this, where this is the structure that marks where the heads and tails are of the A runs, right? So here's an A tail here. Here's an A head and tail, so we put a 1 here. Here's an A head, so we put a 1 here, etc. And then over here, we have a sort of suffix array sample array, so that if you know the rank of this one, you can then go ahead and look up the associated value, which might be the suffix array sample. And we can do this for A, so that we can do predecessor queries like this. Okay, let's look for previous A, boom. And let's also look up the associated suffix array sample, boom. We can do that for A. We could also do it for B. Right? So we need a data structure that, besides just being a predecessor structure, it manages to do this in a way that is conditioned on or stratified by the alphabet characters too. Luckily, we can do this with the exact same structure that I mentioned on the previous slide. It brings in another little factor of sigma. It sort of goes in the middle there. So it's a log sigma plus n over r time query if we do stratify this data structure by the alphabet. Still, that's a minor price to pay, and then the actual space usage hasn't changed. It's still big O of r. So at the end of the day, we store a structure that looks maybe notionally like this. You can see what I've done here is for each of the alphabet characters, I have a sparse representation of where all the run heads and tails for characters, for runs of that character occur. This is sort of conceptually what we want this predecessor data structure to store. And associated with all those heads and tails in this data structure are the suffix array samples that are for the suffix array entries at those heads and tails. So this is the data structure, the only real data structure, complicated data structure that we need to be able to maintain a toehold at every step of backward search. So that is how we do part 1, the maintaining of the toehold at every step of backward search. In the next video, we will see how, given a toehold, we can go outward and we can figure out the locations of the rest of the matches that we are tracking over backward search.